almost forgot to record. It's okay, Cortland. Um, another interesting thing about watching your videos is I finally get to see people's faces for the first time. Because some of you guys never turn on your camera. I've never actually seen your face. So that's good to that's good to associate a face with a name. And so now when I saw Cortland's name, I'm like, I know what she looks like now. Yay. I also like watching the faces you guys make when you take your tests. Some of you guys talk to yourself. Some people pray fervently. I mean, I'm not just saying, Lord help me. I'm talking like they get into it. Stuff like that always makes.
I was nervous that you thought I was cheating because I was talking to myself.
No, it's okay. It's okay.
I like reading out the question. It helps. So I'm not cheating, I promise.
Some of you guys chuckle. Some of you guys talk to me.
I might have yelled at you.
I have talked to you a couple times whenever my computer messes up or the internet. That one day we took that quiz and it just kept videoing me. I really hope you didn't get to see that video because I was so upset the whole time.
But yeah, it's really good that I could finally associate faces with names. Makes it a whole lot easier for me as a teacher. That's one of the things I really miss about in classes is seeing people's faces. I just see names and I have no idea, who's talking to me and who's not. So that's a good thing. I'm finally learning who you guys are. Anyways, back to this. Okay, the largest vessels, the ones that are closest to the heart, the arteries, are called elastic arteries. Now, if you go back to AMP1, elastic means that it's kind of stretchable, it's bendable, but it can also do what's called recoil, which means essentially it can return back to its original position. Okay, whenever you see the word elastic, it basically means that it can bend or stretch, but then once something's going to cause it to bend or stretch, there's going to be some kind of force. But once the force is removed, then something that's elastic will bounce back to its original position. We call that recoil. For example, we have elastic waistbands. I can pull out the elastic waistband on my, boxers. I can pull it out, and then as soon as I let go, it'll snap back into place. That's kind of what happens with elastic structures in the body. For example, your ear. You can bend, you can twist, you can pull your ear, but as soon as you let go, it'll bounce back to its original position. Well, elastic arteries basically do that. Okay. Every time your heart beats, you're going to push out a small amount of blood into circulation, and we call that stroke volume, right? It's the amount of blood that you pump out in a heartbeat, stroke volume. Well, that extra fluid, these arteries have to expand to accommodate that extra little burst of fluid. Now, once that little burst of fluid goes past, then those arteries will recoil back to their small size. Okay, so they're always doing this every time your heart beats. When your heart beats, they expand so the blood can go through, and then once that little spurt of blood goes past, then they'll recoil back to their original position. So they're always doing this with every single heartbeat. And those are called elastic arteries. Now, those are the ones that are very close to your heart, like your aorta, the carotid artery right there in your neck. That's sort of like, an elastic artery. But as you move away, those will turn into what's called muscular arteries. Now, muscular arteries are smaller, and they have a lot of muscle in the walls. That's why they're called muscular arteries. And they also expand and recoil every time the heart beats. So most of the pulse points that you're going to be learning isn't actually the elastic arteries. And if you printed off the notes that I sent you Monday, this bit of information is not in there, but I put it in there later. But if you wanted to add it, you can. If you look where it says elastic arteries, and it says, they allow the rapid transport of blood because they're wide. They're a wider vessel, so blood can move through them really quickly. They maintain a high pressure. And then it says the walls expand during contraction, systole, and then they recoil during diastole. And it says some can be palpated on the surface. Okay, for example, your carotid, you can feel that, and we call that a pulse every time it expands. And we can use that to figure out things like heart rate and stuff like that and blood flow. And then I put below it on the new notes, I put most pulse points that you're going to learn are muscular arteries. Okay, they're commonly called distribution vessels because they're taking blood to the different parts of the body. So you go from elastic arteries, which are really close to the heart, and as you move away, they'll transition into what's called muscular. Now, muscular arteries will also expand and recoil, and those are some of your pulse points. Like you're going to learn the brachial pulse and the radial pulse and the femoral pulse and those guys. Those are muscular arteries. And they are very important for controlling blood flow, the muscular arteries, because we can play with the size of our arteries. We can do what's called vasoconstriction and vasodilation. Vaso is one of the prefixes we do for blood vessels. For example, you've already seen the word vasopressin. You know that the vaso and vasopressin means blood vessels. But vasoconstriction, get used to the words constriction and dilation because you do see those occur a lot in the body. Whenever you have an opening, okay, and the opening we're talking about here is the opening on the inside of the blood vessel, that open space right there, and that's called the lumen, L-U-M-E-N. And so you got hollow tubes. Whenever you have hollow tubes, there's going to be an opening, right? And we can play with the size of that. So we can widen the diameter of that opening, or we can constrict the diameter. And we do it for a couple reasons. One, we're going to talk about now, but then another reason why we do vasoconstriction and vasodilation has to do with blood pressure, which we'll cover on Monday. But essentially what you can do is if you want to restrict or decrease blood flow to a particular tissue, you do what's called vasoconstriction, where you basically make the hole smaller, okay? The reason why is because blood moves faster through a wide tube than it does through a small tube. I mean, that's basic like plumbing and stuff like that. That water or blood will move through a wide tube quicker than it will move through a narrow tube. And so when you shrink up the blood vessels and you reduce the diameter of that hole, then it increases the resistance to the flow of water, and blood and water will not move through that pipe as easily. So we can do that when we want to restrict blood flow to a particular area. We can do what's called vasoconstriction, and that will slow down the delivery of blood to that tissue. If we want to open up blood flow, we do the opposite. So if you want to increase the blood flow to a particular tissue, you do what's called vasodilation, where you make the pipes wider. And where you see this coming into play is especially when you talk about the autonomic nervous system, and you talk about the two modes that your body can go into. You can go into fight or flight mode, or you can go into rest and digest mode. Blood gets diverted to different areas of your body depending on if you're in fight or flight versus rest and digest. I'll show you a little document, or not a document, but a diagram. I'll show you a diagram here in a minute where we can kind of talk about that. Another way that you kind of use blood to one of the other things you use blood for is and we talk about this in chapter 18, is you use it to help maintain temperature. For example, if you go outside, it's actually pretty nice today, but go back to last week when it was, an ice storm and stuff. But when you went outside where it's cold, you will basically restrict blood flow to your extremities, places like your ears and your hands and your toes. And that's why those guys go numb. So what you're going to do is you're going to constrict blood vessels that are leading to your extremities. And at the same time, you will open up blood vessels to your core because you want to keep your vital organs warm. And so that happens all the time when you get cold, is to conserve heat, you'll shut off blood flow, you'll restrict blood flow to the extremities and open it up to the core. So you're kind of playing with the delivery of blood to different tissues. Now there's a word you need to get used to. It basically means the delivery of blood to a tissue. It's called perfusion. And so you might hear that word sometimes in medical shows or in the hospital. That basically means, that blood is making it to that tissue. If somebody has proper perfusion. If something is inhibiting perfusion, that means that blood's not making it to the tissue the way that it's supposed to. And so it basically is just a word we use for the delivery of blood to the tissues and to the capillary beds. Because once you get down past the medium-sized arteries, you get into the smallest arteries, which are called arterioles. So you start out with the big guys, elastic, and they transition into the smaller guys, which are called muscular, and then you transition into the smallest arteries, which are called arterioles. Then the arterioles will lead into capillary beds. And so I put that, it's the third, underneath arteries, it's the third where the arrows are. It says, from the heart, you got elastic arteries, then you got muscular arteries, then you got arterioles, and then arterioles feed into a capillary bed. Now, capillaries are where the exchange takes place between the body and the blood. You got a ton of capillaries. You got way more capillaries than anything else in your body. A couple things about capillaries. These anatomical features that you see with capillaries allows them to do their job efficiently. Cucumber, 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 cucumber. Do you guys know that? I don't know why it works, but it works. If you feel like you're getting ready to sneeze, just say cucumber over and over again, and it stops you from sneezing. I don't know how that works, but it does. But blood vessels, capillaries is the place for exchange between the tissues and the body, in the blood. And so you got to maximize that. You got to be as efficient as you can. You don't want an exchange in your arteries or veins. That's not good. But you want the exchange to take place in the capillaries. And so one of the things you see with capillaries is that they're very, very, very thin. Okay, very thin. If you take a human hair, just look at one of your hairs, just pluck a hair out and look at it. Okay, capillaries are 1/10 of the size, 1/10 of the size of human hair. Okay, very, very, very thin. The diameter of a capillary, if you remember, go back to blood. The diameter, the lumen, the opening of a capillary is just wide enough to allow a red blood cell to go through one at a time. We watched that video on that. So they're extremely thin, okay? And what that does is blood can't move through it quickly. It's going to slow down blood. So blood goes really slow through a capillary bed. And that gives you time to drop off. The blood can drop off what it needs to, and it can pick up what it needs to. That's where the exchange takes place. And so that's one thing that kind of makes it good at its job, is this very, very, very thin diameter. The enormous number of capillaries. There's a huge, there's miles and miles and miles and miles of capillaries in your body. If you took all the capillaries in the body and you laid them end to end in an adult, let's say average size adult, if you took all the capillaries and attached them end to end, it'd be about 100,000 miles. Now, the circumference of the earth is a little over, it's just a little bit over 24,000. So it's like 24,000 something miles. Okay. So that means if you take, if you take 100,000 miles of blood vessels and link them end to end, it will go around the earth at least 3 times. It's crazy to think about that. But there's enough capillaries in your body to go around the world 3 times, and possibly even 4, depending on how big you are. You really see just how much blood vessels you have when you look at plastination. I don't know how many of you guys are familiar with plastination, but it's a preservation technique where they will take a cadaver of some kind, whether it be a human, a shark, a bunny rabbit, a horse, or whatever. They'll infuse into the blood, they'll infuse a polymer that, when it hardens, it essentially turns into plastic. And they call it plastination. And you might have seen these pictures before, like in books, okay? But it'll show somebody sitting there like playing tennis, and it's like a plastic model, but that actually used to be a person. It's somebody who donated their body to science, and they used it for plastination. But plastination, let's kind of bring up plastination of blood vessels. So they inject this polymer into the blood, then they let it harden, and then after it's hardened, they will either just let the tissue rot away, or they will use some kind of chemical to dissolve the tissue, and then what you're left with is a perfect cast of the blood vessels. And it really allows you to see just how vascularized the body is. I mean, if you look at the head right there, that's all the blood vessels that's in just the head. The head is loaded with blood vessels, capillaries, because you have all your sensory structures up there. And then also your face is very sensitive to touch. So you got your nose, your eyes, your mouth. All those guys need a nice blood supply. You got your brain, which needs a really good blood supply. So that's somebody who donated their body to science. They infused them with that polymer, let it harden, and then dissolve the actual tissue away, and you're left with a cast of blood vessels. That's really neat right there. So all the blood vessels you see on these pictures that kind of look like cotton candy, those are capillaries. You just got millions and millions and millions and millions of capillaries. All right, there's the brain. The bigger blood vessels there would be like arteries and veins. And then when you get out here towards the periphery, where it looks all fuzzy like cotton candy, that's capillaries. Plastination is really cool. They have these exhibits. It's called Bodies Revealed, but they have these traveling exhibits, and there's some permanent ones too. I think there's one in Las Vegas that's like a permanent exhibit of Bodies Revealed. But they do this kind of thing with plastination. There was one in Myrtle Beach a few years ago. I don't know if it's still there, but it was kind of like it was there for a short amount of time. And they actually came to Gallipolis, Ohio, about 4 or 5 years ago. The Bodies Revealed exhibit came to those areas. Here's a chicken. So there's a bird and all the blood vessels that are in a bird. Here's a rabbit. There's a rabbit that's been plastinized. There's plastinized lungs. Now that's the respiratory tree. We're going to talk. That's not blood vessels. That's actually the pipes inside the lungs. So you can plastinize blood vessels. You can plastinize the pipes in the lungs. You can plastinize the entire body. It basically pushes out the fat. It replaces the fat with plastic, and then you let it harden. You can pose the people into different poses. You'll see them playing like tennis and boxing. And oh, there's a horse's head that's been plastinized. So it shows you there some of the blood vessels set up. But look at that. Look how much your body is loaded with blood vessels. And the reason why is because every cell in your body needs to have riverfront property. Okay. There are some cells that are located a little bit of a distance away from blood vessels because some body parts are what we call avascular, which means they don't have a direct blood supply, like epithelial tissue and cartilage. Okay, those guys, they don't have a direct blood supply, but they still need to be close to the blood to receive nutrients through diffusion. And so most cells, though, have riverfront property. They're actually associated with a capillary bed. And I think I read somewhere before that, like 99% of the cells in your body are less than a 0.5 millimeter, I think, from a blood vessel. So they're very close to a capillary bed, about less than a 0.5 millimeter from a capillary bed. This one's pretty cool. Here they actually use 2 different collars, and so the blue they infused into the areas that have oxygen, deoxygenated blood, and the red they infused into the areas that have oxygenated blood. So you can see the right atrium is blue, and the left atrium is red. That's really neat right there. Here's somebody who donated their body to science. They plastinized them, and now they're on display somewhere in a certain pose. It's really cool. Oh, how far we've come. Back in the day when they would dissect a specimen, you had to get rid of it pretty quickly because it would start to rot. But now, we developed preservation techniques like formaldehyde, and then we moved up to formalin, and now we have plastination. And so these plastic models will last a very long time. There's a shark right there. There's a shark, all the blood vessels in a shark. So if you donate your body to science, you may end up as part of a Bodies Revealed exhibit.
Do they last like forever, or do they eventually like get out?
Well, I mean, anything would eventually break down, but they would last an extremely long time. I mean, we're talking hundreds of thousands of years. I don't know about that particular type of plastic. The average plastic, like the stuff we have in our house, the average plastic has a half-life of somewhere around 4,000 years, which means if you throw a bottle of plastic out into the environment, it would take about 4,000 years for half of it to degrade away. Different plastics degrade at different rates, okay? But like average plastic is about 4,000 years. So yeah, this would last a very, very, very long time. I wouldn't say forever, but yeah, that's just me not wanting to say something absolute. They would last a very, very, very long time. And of course, if you put them in the right environment, they would last even longer. That's neat right here. So there you can see actually the major arteries and blood vessels. That looks like the major arteries in the body. So they probably put something to cut it off at the capillary bed, infused it in, and then just plastinize the arteries. And then you can do the veins somewhere else, or with another person, that sort of thing. So if you're thinking about donating your body to science, you could be turned into a plastic model. Actually, there's a really cool book that I do recommend for people. I actually like this author. Her name's Mary Roach, and she writes a lot of books about science, but she writes them in a layman's term type. I mean, she does use technical language from time to time, but she also puts it in a way that even if you didn't have a lot of science knowledge, you can read it and kind of have an understanding. But if you do have knowledge of whatever it is she's talking about, it's even better. But I have a book of hers called Stiff, and it's called Stiff: The Curious Lives of Human Cadavers, where it's a book about what they might do with your body if you donate to science. You may go to a body farm where they study decomposition. You may go to a cosmetic school where they practice, or a plastic surgery, where they practice plastic surgery on your head, because once you relinquish control, they can do whatever they want with it. They can strap you in a car and run you against the wall to test crash damage. When you donate your body to science, it goes wherever it can be used. They may test the explosive ability of dynamite on you. Just stick dynamite in you and see what happens when you blow a body up. And so this is a really cool book, though. I really enjoyed reading this book. So if you get a chance, go to Books A Million. It's probably pretty cheap now, just because it's been out for a while. I've read that one. I've read Bonk, which is a book about reproduction. It's not so much about reproduction as it is about the act of reproduction. And so it talks about what happens when you are intimate with somebody else and some of the research that's done. I don't know if you've ever seen the movie Kinsley with Liam Neeson, but it's a book about this guy who used to do these experiments with couples. He would basically have them do the deed, and he would have them hooked up to like heart rate monitors and blood pressure monitors while they did it, and he would do research on them. And so he's actually in that book. And what's funny is his number one assistant, Kinsley, his number one assistant's last name was Pomeroy, which I thought was funny because that's my last name. Yeah, this is a movie if you get a chance. It's a 2004 film, but it's called Kingsley. And it's about this scientist who, that's what he basically studied, was Liam Neeson. There we go. He studied people being intimate, like scientifically. He would measure their temperature. He would measure their their behavior during it. So basically they would do it right there in front of him. He'd be sitting there with his like little notepads taking notes about what happens and stuff. Seems very, very awkward, but he would do that. And so that book, there's a section in that book about that, of his studies, and actually mentions who I'm going to say is my ancestor, some guy with the last name Pomeroy. She has a book called Grunt, which is about what happens to your body physically and mentally when you are in a military wartime setting. Things like panic and exhaustion and heat and stuff like that. They're really good books. I've read actually all three of those. She does the science. She talks about the science. She talks about the physiology. She talks about the anatomy, but she does it in a very smooth way to where it's a very easy read. You know, I mean, it's not like you're sitting there going, "Gosh, this is tedious." No, the way she explains things is very, very good. And so I recommend her to my students. If you're interested in reading about science, the interesting things about science, and especially the human body, then she's definitely an author you'd want to check out. I have those 3 books actually on the bookshelf right now. And she's done a few more too. Yeah, her name's Mary Roach. The one about plastination is called Stiff, The Curious Lives of Human Cadavers. And so if you're thinking about that, you might want to check out that book, see what they might use you for.
I did. I just looked it up and I just ordered it actually. It's only $14.
Yeah, it's you can probably find it used a lot cheaper.
Yeah, for use it's like $9
Yeah,
on Amazon.
it's a really good book. I enjoyed it. It's been a while since I read it, but it's kind of cool some of the things she talks about in there. Because we have to know how stuff's going to affect the body. So a lot of times we just use people who have, cadavers, and you just do it. They use it a lot for those crash tests. You may start out with a crash test dummy, but eventually you want to see what happens with an actual human body. You might get strapped in the car and then ran against the wall at 100 miles an hour. On the other side of the capillary bed is your veins. Okay, they actually start out small. The smallest veins are called venules, and they actually get progressively bigger as you move back towards the heart. So you have what's called venules. They will merge together into bigger veins. They're just called medium-sized veins, and those guys will merge together into bigger veins. They're called large veins, and then eventually you make your way back to the heart. So arteries lead to a capillary bed. Blood moves through the capillary bed, goes into veins on the other side, and makes its way back to your heart so you can do another circuit. Blood pressure, we got a lab one, so let's not worry about that right now. We will come back to this, though, when we do that lab. We'll talk about blood pressure. One of the things I do want you to make note of for what we're going to talk about here in just a little bit is that the pressure, blood pressure, in arteries is a lot higher than veins. Okay, veins have extremely low pressure. You can actually see it here, down here in the bottom. So if we blow this up right here, this graph at the bottom shows what happens to blood pressure as you move from arteries to veins. So as blood moves through the capillary bed, which is right here, the pressure drops off a cliff. Blood moves a lot easier through arteries. Okay, blood has trouble moving through veins. That will come into play here in a minute. And one of the things that makes it hard is just the low pressure, extremely low pressure. I mean, it drops from 100. When you think about blood pressure, 120 over 80. The average blood pressure of an artery is about 100. The average blood pressure in a vein is like 2. It goes from 100 to 2. And so the pressure inside of veins is like 50 times lower than the pressure inside arteries. And that's why blood has trouble moving in veins. It tends to pull. It tends to clot in your veins because it doesn't move very well. That's part of the notes that we'll get to. Let's go to capillaries first, though. So let's talk about capillaries before we talk about veins. Capillary dynamics is basically just what is happening at the capillaries. What is occurring, where some components of blood have to leave, but then they have to be pulled back in. So they kind of leave and deliver things to the tissues, then they have to get sucked back in, and that's pretty much what capillary dynamics is. So this is all stuff we're going to do. The pulse points, the blood pressure, that will come in the lab on Monday, so you don't have to worry about that right now. We talked about this, okay? Not only are capillaries in general very thin, but the walls are also extremely thin. And that allows things to very quickly move in and move out. So that's kind of another characteristic of capillaries that makes it really good at exchange. It's very thin. It's got very thin walls. There's tons of them, and they branch like crazy. And that branching increases surface area. Whenever you increase surface area, that makes it easier for things to be exchanged. So all these anatomical characteristics that you see with capillaries makes them really good at their job. That's where exchange should take place. And it should be as efficient as possible. When you have blood move through the body, you don't want to waste any opportunities. You want to make sure that all the tissues get their blood, and you want to make sure that you can pick up whatever's being produced by those cells that have to be removed from the body, like waste products. Let's look at capillary dynamics. I actually like to draw capillary dynamics because it helps to come. But here's capillary dynamics right there. This is number 1 on the notes. I'm going to pull up a whiteboard and kind of show you something here. All right. Let's do some color coding. Here comes the blood. It's coming into the capillary bed. We'll move it over here like that. I'm just going to draw one capillary, but just understand this is happening for all of them, okay? And then about halfway across, let's transition to veins. And then let's return the blood back, okay? So blood's going to come in this way, and it's coming in through the arteries. So this will be an arteriole over here. And then it will feed into the capillary bed. It will come across and then leave this way. And that would be the smallest veins in the body, which are called venules. We call this over here the arterial side. And this is called the venous side. So arterial side here. That's the arterial side of the capillary bed. And this is the venous side of the capillary bed. Now, not everything in blood leaves. Okay, there are always going to be some things that are not supposed to leave the blood at the capillaries. And the main driving force, because some things are going to have to come in and actually leave the blood and go into the tissues. The main selecting mechanism that determines like what leaves and what stays behind primarily is size. Smaller things get pushed out. Larger things stay inside the blood, okay? So what you're really looking at is you're looking at the plasma fluid. Remember that plasma is like water-based, and then you got things like nutrients in it, you got salt in it, you got electrolytes, those kind of things. Those are what leave. Okay, so plasma should get pushed out over here. Now, what's pushing it out is blood pressure. And what they call this is filtration. So filtration happens on the arterial side of the capillary bed. And the driving force is blood pressure. On the venous side, that plasma needs to be pulled back in. So the arterial side is pretty straightforward. Blood comes in at a high pressure, and that high pressure will push things through the wall. And that's called filtration. Things that stay behind, things that are not supposed to be pushed out, are red blood cells. Okay, so here's some red blood cells here. They should not leave the blood under normal circumstances. But then there's another substance that doesn't leave. Okay, go back to plasma. Plasma is water, electrolytes, salts, nutrients, waste products, okay, all that. But there's also these things we call plasma proteins. And go back to, and this is what you have to know this for the test, is there's a particular plasma protein that you hear a lot when it comes to the osmotic pressure of blood. Anybody want to give that to me? Which plasma protein do you usually think about? Who's the important contributor to the osmotic pressure of blood?
Albumin.
Albumin. That's right. I'm going to put albumin over here, okay? He's the most abundant plasma protein. There's other ones like globulins, antibodies, things like that. Well, think about this. These substances, your red blood cells, your albumin, your other plasma proteins, they're supposed to stay in the blood. They don't leave here. They don't leave at the capillary bed. What is leaving is the watery part of plasma. A lot of water is leaving. So what happens is, as blood moves across the capillary bed and that water is leaving, that means that on the other side, on the venous side, that's going to be a more concentrated blood. And the word we would use is hypertonic. Okay, so let's put in a bunch of, how do you concentrate something? Remove the water. Okay, so water's leaving here. And so as water, the blood's going to continue to move across the capillary bed. Water's leaving. And so as the blood moves across, it becomes more hypertonic because of the solutes. The solutes in this case are red blood cells and albumin. Okay, anything in water is a solute. And so red blood cells are a solute, albumin's a solute. And so as you move across, the concentration of the blood becomes hypertonic. Now you've got what you need for osmosis to take place. Remember, you have two criteria that needs to be met for osmosis to occur. One is you have to have two water-based environments that are separated by a membrane. And that's your membrane there. Okay, the wall of the blood vessel. And then you need to have a difference in concentration. When you have those two things, water always gets sucked towards the hypertonic environment. The saying is solutes suck. So as it moves across the capillary bed and the blood becomes more hypertonic, it's going to suck the water back in. And then whatever's in that water will get pulled back in as well. So that's called absorption. That happens over here on the venous side. Absorption. And so that's going to be by osmosis. So blood leaves at the beginning of the capillary bed. It leaves because of blood pressure pushing it out. And then on the other side of the capillary bed, it's getting sucked back in because of osmosis. Now this brings up, does that make sense? Are we okay here? Anybody have any questions about that?
No.
If your blood pressure is abnormal, that affects capillary dynamics. If your blood pressure is really high, that'll push out a lot more fluid into the tissues than would be normal. And so a lot of times when somebody has high blood pressure, they'll start getting edema, fluid buildup in places because the blood pressure is so high that it's pushing out a lot more plasma than it usually would. If your blood pressure is low, that's going to affect capillary dynamics. That means that less plasma gets pushed out on the arterial side than it should be. So blood pressure, because it is a factor in the delivery of plasma to your tissues, if you have abnormal blood pressure, that's going to disrupt perfusion in some way. If your albumin levels are not where they're supposed to be, that will affect the osmosis that has to occur to bring the plasma back in. And so if somebody has, let's say, some type of liver disorder, because that's where albumin's produced is in the liver. If somebody has lost a lot of plasma proteins due to things like hemorrhaging, or if they have liver problems where they're not able to produce as much plasma proteins as they should, that'll mess with capillary dynamics. Same deal, if you have less albumin, then you won't get that good hypertonic environment. And so essentially more fluid's going to get pushed out on this side than gets pulled in over here. Now that does happen naturally, but when you're low on albumin, that makes it even harder to pull it back in on the venous side. And so a lot of factors kind of go into capillary dynamics. You got your blood pressure, you got your solute concentration of your blood. Dehydration can mess things up because it plays with it plays with the solute concentration of your blood. If it's efficient, you'll push it out. It'll bathe the tissues. It'll deliver what it needs to. It'll pick up what it needs to, and then it gets sucked back in on the other side. So that's kind of the recap of number one right there. It says, capillary dynamics refers to the factors that influence the exchange of fluid between the blood and the tissues. On the arterial side, that's over here. On the arterial side, plasma fluid is pushed out because of blood pressure, and it goes into the tissues. Now, here's a word you're going to hear several times this semester: interstitial. Okay, interstitial is the word we use for tissue space or tissue fluid. So if you hear interstitial space, they're talking about the space in the tissues. And if you hear the word interstitial fluid, they're talking about the fluid in the tissues. So that's going to be this fluid out here. So if you think about it, for a brief moment in time, interstitial. Okay, so that's the tissues. We call it interstitial fluid. For a moment in time, plasma fluid, okay, that's basically plasma without the proteins, because the proteins stay in the blood. Plasma fluid will become a part of interstitial fluid. And then it's supposed to be drawn back into the blood and return to being plasma again. So it's kind of like plasma gets pushed out, it becomes a part of interstitial fluid, and then some of that's going to get drawn back in, and it's going to become plasma. Okay, plasma. We talk about this a little bit later, how plasma and interstitial fluid are very similar to each other as far as their composition, because plasma becomes interstitial fluid. The only difference really is the proteins. Plasma has more proteins than interstitial fluid because proteins are not supposed to leave the blood. Look at that last note there, though. Oh, but first, it says plasma proteins don't leave the blood. Blood becomes hypertonic due to albumin and other proteins as it moves across the capillary bed. On the venous side, so that's over here, on the venous side of the capillary bed, plasma will get pulled back in because of osmosis. So some people remember like a bus ride. You push the kids off the bus with blood pressure, filtration, and then you bring them back in on the bus with osmosis, absorption. Notice that last statement there, F, under number one, F. More blood is pushed out. Okay, this is always. Blood pressure is higher than osmotic pressure. Okay, and so more blood gets pushed out on the arterial side than gets pulled back in on the venous side. And so you actually lose fluid in the blood as it moves across the capillary bed. So you push out more fluid here, then you draw back in fluid there. And so there's more fluid over here than there is over there. That happens no matter who you are. It's just capillary dynamics. Now that comes into play, though, this whole idea of at the capillary beds, you're always pushing out more fluid than you're pulling back in. That's going to come into play with the lymphatic system next week. I put a little blurb there on your notes about the lymphatic drainage. But basically what it says is any plasma that doesn't get returned, okay? So you push out the plasma, and some of it's going to get sucked back in, but not all of it. Some of that plasma is going to stay behind in the tissues. When that happens, that plasma just becomes a part of interstitial fluid. And I mean, it becomes more of a permanent part. Yes, it happens down here where you have, plasma leaves, goes into the tissues, but then it gets sucked back in. But if it doesn't get sucked back in, it becomes more of a permanent part. Cucumber, 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 cucumber. See, I'm telling you, it works. I don't know why, but it works. I was very close to a sneeze right there, but I was able to hold it back. But plasma goes in and becomes part of interstitial fluid. Now, here's where the lymphatic system comes in. If you let that happen, okay, so think about this. fluid is slowly accumulating in your tissues because you're always pushing out more blood than you're pulling back in. So what you need is you need a way to vacuum up that fluid, that excess fluid, and return it back to the blood. And that's where the lymphatic system comes in. Any plasma that doesn't return into the blood on the venous side becomes a part of interstitial fluid. And then that fluid gets picked up by the lymphatic system and it gets returned back in the blood that way. And so that will come into play when we get into the lymphatic system next week. Kind of ran out of room right there. And so I put covered in chapter 21. Let's not worry about it right now, but it will come into play later. Once the blood gets pulled back in on the other side, it's going to start making its way back to the heart. All right. And we call that venous return. And in general, venous return is difficult. Okay. For a number of reasons. Blood does not move very well in the vein. And so let's go back to the PowerPoint. We all cool here? Anybody have any questions about this? Capillary dynamics. Push it out with pressure, pull it back in with osmosis.
No, we're good.
I'm looking for my share screen thing. Got like 3 drop down boxes. There we go. All right, so there. So here's the point that will come into play next week. More fluid is forced out than is pulled back in. It actually explains something here in a second. It's one of the reasons why blood is so hard to return back to the heart. So the thing about veins is that blood doesn't move very well, okay? It tends to get stuck. It tends to get bogged down. It even tends to collect in certain areas of your body. And so most of the blood that's in your body right now is actually in your veins because it kind of gets stuck there. So, you have no problem with blood flow in your arteries because the pressure's high. You have a propelling force, which is the heart. So the heart's always pumping to push the blood forward. So having a clot form in the arteries is kind of rare. Okay, you usually associate aneurysms with arteries. Aneurysm is when you have a weakening of the wall of a blood vessel. And it can actually bulge out and possibly even rupture. That's what an aneurysm is. An aneurysm is more common in an artery because of the high pressure. The high pressure weakens the wall over time. All right. And plus just age. Age a lot of times will weaken the wall of your blood vessels. So you typically associate aneurysms with arteries. And you typically associate clots with veins. I guess another thing you may want to put is like plaque buildup. We usually associate plaque buildup with arteries. So usually when you hear about aneurysms and you hear about plaque buildup, they're usually talking about the arteries. It doesn't mean that you can't have an aneurysm in the vein or you can't have plaque buildup. Okay, it's just saying that usually when you talk about it, you're referring to arteries. When you're talking about clots forming, you're usually talking about veins, because the blood just doesn't move very well. And whenever blood doesn't move very well, the instances or the chance of clots happening increase. So notice what it says there on the PowerPoint. Most of the blood in your body is in your veins, that second point right there. And in veins, their job is to get the blood back to the heart, and it's difficult. They have to overcome a few things. So we call it venous return. It's the amount of blood that the veins deliver back to the heart. So I put on your notes that venous return is number 3 on your notes. Venous return is difficult for several reasons. One, in general, the lumen, okay, not the vessel, not the whole vessel, but the lumen, the opening of a vein is generally larger than an artery of the same size. So if you had an artery beside a vein of the same basic size, the lumen, the opening in the middle, is typically larger in veins. That's one of the things that keeps the pressure in arteries high, is the narrow lumen. So you got a wider diameter in veins. Now, we talk about this next week. Whenever you have a pipe with fluid in it, The wider the pipe, the lower the pressure. So veins basically have wider pipes, not the overall pipe, but the lumen, okay? What's actually holding the fluid. So that wider radius, the wider lumen, means the pressure is going to be lower. And then there's less fluid in the veins because more fluid gets pushed out at the capillaries and it gets drawn back in. So as blood moves across a capillary bed, you actually lose fluid. Fluid is also a primary contributor to pressure. And when you lose fluid, you lose pressure. So that's another thing that drops the pressure. The walls of veins are more elastic. They're more loosey-goosey. You know, they're not as tight as arteries are. The walls of arteries are very tight to where, you know, you get that boom, 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 boom. The venous return is the venous wall is just more loose. It's more loosey-goosey. That also drops the pressure. So when you take those three things into account, that explains why, you know, the pressure in veins is so much lower than the pressure in arteries. If you go back to that picture right there, okay? Pressure is a driving force of blood flow. The higher the pressure, the faster blood moves. The lower the pressure, the slower blood moves. So that's one reason why blood doesn't move very well. Now, if you look at Roman numeral 5, where it says other factors, these are other factors that make it hard to get blood back to the heart. One is there's no heart propelling the blood forward. Okay, there is no problem with blood getting pushed forward in the arteries because, you know, the heart is pushing it forward. We talked about that a little bit, that blood, as blood moves through number 2 there, as blood moves through a capillary bed, it slows down. So basically you lose the momentum. There's always momentum, blood pressure pushing blood forward in the arteries, but not so much in the veins. And then gravity. Gravity is a big deal. Because if you think about it, when you're standing up, where's your heart located at? In your chest, right? When you're standing up, and let's say your arms are down by your side, which they are a lot, right? When you're standing up a lot, you don't usually have your hands up here. Your hands are usually down by your side. Most of the blood that's coming back to your heart is actually going up, okay? Like the blood that's in your arms are going to have to go up your arm, into your shoulder, and then go back to the heart. And then everything below the heart is going to have to go up to get back to the heart. Well, gravity pulls things towards the ground. And so the blood that's coming back up, trying to make it back to your heart, is fighting gravity. So gravity likes to pull the blood towards your feet when you're standing up. And so what happens is all these factors together, blood moves extremely slowly through the veins. And blood tends to collect in certain areas of your body, especially the lower body. Okay, it'll collect in those areas. And so I put with Roman numeral 6 right there, due to all those factors, you know, low pressure, you got your gravity, you're fighting gravity, you have no heart pushing the blood forward. Okay, all those factor in to blood moving slowly through your veins. It's a very slow process. And so blood will pull in certain areas, like your feet, your legs. And when that happens, when blood doesn't move very well, the risk of blood clots goes up. So that's kind of that's some of the most common places that blood clots form is in the lower body because of gravity and blood's not moving very well and all that. Actually, on Monday, we're going to talk about a blood vessel. Okay, I want to talk about blood vessels first, but we're going to talk about a blood vessel. So we're going to continue with this Monday, this whole venous return story, because there are some side stories that kind of go along with it. But we can at least get the gist of it right now, and then we can add on to it on Monday. But there's a blood vessel in the back of your knee. It's called the popliteal vein, okay, and it's bringing blood back towards your heart. When you bend your knee, that vein kinks like a water hose. So you know how you get a bend in a water hose, a sharp bend, and the blood can't go through the water hose wherever you have a kink at. Well, every time you bend your knees, that blood vessel kinks a little bit, and the blood can't move through it as well. And and then the blood clots like to happen in that area. So what we have to do is we have to help blood get back to the heart. And so you'll see some things associated with veins that you don't see associated with arteries. One is valves, okay? Your veins actually have valves in them, similar to the valves that are in your heart. You know, valves in your heart will open up to allow blood through, then they shut back again, right? Or they open up this way, allow blood through, and shut back. Your veins do the same thing, okay? You don't have any valves in arteries. You don't need them, okay? Because the pressure is really high, the blood's always moving. Arterial flow is not difficult under normal circumstances. Venous return is always difficult no matter who you are. But it's even worse for people that have circulatory problems and things like that. So we all have these valves, and essentially what they do, now, let's say blood's coming up. So blood's coming up to the heart. These valves will open up, allow the blood to go past, and they shut so the blood can't come backwards because gravity is always pulling it down towards your body. There's actually a video I'm going to show you here in a minute that kind of brings this into play. And so we all have valves, okay, but some people, their valves are quote unquote leaky, okay? Their valves don't shut properly. So imagine that a typical valve's supposed to do this, but for some reason their valves don't shut the way they're supposed to, or maybe there's a gap there between them. And so every time they push blood through the valve, it'll kind of just get pulled back down. So blood's kind of doing this in your veins. It's getting pushed up a little bit, and then it comes back down. It's like 2 steps forward, 1 step back as it makes its way back towards your heart. So let's kind of watch this video right here that shows you what happens when you have leaky valves. What happens over time is blood gets pulled down towards your feet and towards your legs, and it will cause your veins to bulge out because your veins will be holding more blood than they should, and it will cause the veins to become swollen. It'll cause them to bulge. They'll become deformed, and we call that varicose veins. And if you look up varicose veins on Google Images, you'll see some really bad pictures of varicose veins, okay? That's what happens when blood gets pulled down towards your lower body. It starts to collect in your veins, and it will cause them to bulge out. My wife has pretty bad varicose veins in her legs, especially when she was pregnant. She got really bad varicose veins. And she's actually had to have ultrasounds done on them to make sure that there weren't any clots and, make sure that the blood was okay, that sort of thing.
I have horrible ones, and my mom and my brother do too. My brothers are really bad.
Well, that's kind of interesting because males usually don't get varicose veins as easily.
Oh, his are horrible. Like, he's had to have them looked at like 7 or 8 times. Like, they even want to do a surgery on one of them. It's so bad. It's really
that sounds
bad.
genetic. You know what I mean? Like it's your family's just predisposed.
Mm-hmm.
Maybe your family has leaky valves. You know what I mean?
Yeah.
It runs in my wife's family. I mean, she has varicose veins. Her grandma had varicose veins really bad when she was alive. And so, yeah, it's something that typically is hereditary or can be hereditary. It's also usually seen at a higher incidences in females than males. Now, if you have a poor circulation, you'll also see it more often. My dad, he's 74 years old. He's diabetic. He has heart disease. He has heart problems. He has a bypass done. He has a defibrillator in. So my dad has heart problems. My dad's diabetic. He's got really bad varicose veins in his feet and legs. So yeah, you will see even males, depending on how their health is and their age, that kind of comes into play. I don't know how old your brother is. If he's pretty young, then yeah, that makes you think that it's something genetic that's causing that.
He's 39, but my grandpa had him, my mom had him, and then I'm 40 and I have him. But mine aren't, like I said, mine aren't nearly as bad as his. Like, I have one that I can't stand, but he's got them. Like, you can just they're like really like pronounced.
Yeah, firm to the touch. A lot of times they're firm. Yeah, a lot of times they're firm to the touch too.
I'm not touching his leg. No, I'm just kidding. They don't look good though. But yeah, he even had to go see like 2 different surgeons because at one time they wanted to try to like remove it or do something to it. I don't know. He's even had salt water put in him. If that's even
Here's
strange.
that video. Let's blow this up just for a second here. There's a woman talking, but I just looked up varicose veins and valves. Here we go. All right, so right here is kind of what's going on. Now, you see the red on the 2 sides of the vein? That's muscle. That's the other thing. That's the other anatomical adaptation that helps to sort of move blood back to the heart. Your veins are flanked by skeletal muscle. That's voluntary muscle, okay? So whenever you contract those muscles in your legs and your arms, those muscles will actually squeeze on veins to help move blood back. And so activity, exercise, things like that help to push blood back towards your heart because your muscles will actually squeeze on the veins and push it forward. So these little red things over here, these are muscle fibers. And when they squeeze on the vein, right there, it pushes blood forward a little bit. It's just a little spurt, okay? Then notice that the blood kind of wants to get pulled backwards. And so you push it forward, and then it kind of gets pulled back a little bit. It's just kind of moving forward in a step-by-step sort of fashion. Now, that's what's supposed to happen. And then when you have varicose veins, let's move it forward just a tad, right here. All right, so watch what happens when you have varicose veins. The valves will open, but if they don't shut properly, then the blood gets just pulled back down again because gravity's pulling it down towards your feet. So you might push a little bit up, and then it's like you're making no progress. It's like 1 step forward, 2 steps back kind of deal. Now, notice what's happening with the blood cells. They are not moving. Okay, they basically are stopping. Especially these guys that get caught over here in these corners and stuff. If you watch there, the red blood cells are basically collecting in those areas. And whenever blood collects in those areas, the risk of clots are going to go up. Okay, anytime blood slows down, stops moving, goes backwards, any of that, that's what causes the increased risk of blood clotting.
After time, if you don't get it like taken care of, will it turn into a blood clot?
It could, yeah.
Okay.
Very much so. And that's why she's talking about sometimes they'll do surgical surgery on it. They might put you on blood thinners. If you have really bad varicose veins, they may put you on blood thinners. The deep veins, if it happens in the deep veins, that's the ones that they're really worried about. Okay, that's deep vein thrombosis when you get a blood clot in the deep veins. What they're showing you here is what's called superficial veins. Okay, superficial veins are the ones that's closest to the surface. They're the ones you can see. Okay, so in this picture right here, the superficial veins are in the light blue, and the deeper veins are in the dark blue. You can get blood clots in the superficial veins, and they tend to, they're not as dangerous than the deep veins. The deep veins are larger. And so blood clots that form in superficial veins, a lot of times get caught in the superficial veins, and they don't really detach and move somewhere else. It's typically the deep veins where you'll get a piece that breaks off, travels to your heart, gets pumped to your lungs, and causes a pulmonary embolism. And that's why they call it deep vein thrombosis, DVT. All right, that's the dangerous one, because those are the ones that typically break off and make it back to your heart versus the superficial veins. Superficial veins are a lot smaller, and there's a lot of places where they can kind of get caught. It doesn't mean you can't have a blood clot in the superficial veins that causes problems, but the deep veins that's where the problem really happens. And so that's what happens right there. It says, many veins in the body are flanked by skeletal muscle. They squeeze on the veins when they contract, and they call it the skeletal muscle pump. Just give me like 2 more minutes or 3 more minutes, we'll be done for the day. So they'll basically squeeze every time you contract a muscle, they'll squeeze. That's why exercise is important. All right. Inactivity, sitting down for a long time, laying down for a long time, all that slows down blood in your veins. And then I told you earlier, like that blood vessel that kinks when you sit down, that's also, if blood gets caught in that kink, then the risk of blood clot goes up. What happens a lot of times is people will sit for a long period of time. That blood vessel, the popliteal vein, will kink, they'll get a blood clot form at the kink. Then when they stand up and it goes back to being straight, that's when it starts moving. It's actually very common for people who have been sitting down for a long time to form a blood clot in their leg. Then when they get up and start moving around, the blood clot will start moving. And then it will make its way back to the heart, get pumped to the lungs, and next thing you know, they're dead. There's been many of people who have developed a pulmonary embolism from a long plane ride where you're sitting for a long period, or a long car ride. You know, you should always, when you're on a long car ride, you should get out. It depends on how, your health is, but even if you're very, very healthy, you should get out at least once every couple hours. Stretch your legs, move your legs, contract your muscles, walk around, because the longer you sit, the higher the risk of clotting occurring. If you have poor circulation, they recommend you stop the car every hour and get out and walk around, because the longer you sit, the worse it gets. If you have a job that requires you to sit down for a long time, you gotta be careful. That's why we give breaks now. That's why they have those desks that you can stand up and you move the desk up and you can do your work standing up. Because the longer you sit, the chances of blood clots forming increase. And then it can turn into a pulmonary embolism. So I kind of gave you some things down there at the bottom, things that can put you at risk of DVT and subsequently pulmonary embolism. And we're going to talk about this more Monday, because I do want to expound on some of these things. I worry with me, honestly, because I sit cross-legged on my bed when I teach. And so you might see me every once in a while kind of shift my weight. Right now I have my right leg stretched out. You can't see it. But a lot of times I have my legs crossed, and so my knees are bent, and they could be bent like that for an hour and a half or so. I'm just, I hope we don't have to do this very much longer, because I don't have a desk in my room. The kids got all the desks. I don't have a desk in my room I can sit at and do it. Plus, having the desk, you can kind of see too much of my room, and I don't want you to see too much of my room. So I sit on my bed when I teach, and I have my legs crossed, and I always wonder about, blood's not moving very well. So sometimes I'll just grab my foot and do a little exercising with it, just kind of work my calves, get them going. But that's what it says, long plane rides, long car rides, binge watching TV. They actually call it binger's thrombosis. It's like where if you sit there and watch a complete season, 20 some episodes over the weekend, and then you just sit there and watch it, that means you're sitting for a very, very, very long time. And that's what kills you about like Hulu and Netflix and stuff, is one episode will end on a cliffhanger, and you're like, I can't wait, I gotta watch the next one. And then that next episode will end on a cliffhanger, I gotta watch the next one. And the next thing you know, you've watched 10 straight episodes and you haven't gotten off the couch in 5 hours, But they actually have what's called binger's thrombosis now, where you can form a blood clot in your legs from sitting down and watching TV too long. If you sit down and play video games for too long, that's called gamer's thrombosis. They're worried about like teenagers developing blood clots from playing video games too long. I mean, I love video games as much as the next person. I might play for an hour or so, but there's some people who they will play for 10, 12, 14, 18 straight hours. You see stories of people collapsing from exhaustion from playing video games for too long. And a lot of times you see it in these video games where even if you leave the game doesn't end. The game doesn't stop, right? So you have these worlds where somebody's always playing in that world. And so, if you leave the game, other people can stay in the game and keep playing, and you're always worried about them getting an advantage or stealing your stuff or whatever. So some people get in that kind of zone where like, I can't leave the game, I can't leave the game, I can't leave the game. Or I don't want to leave the game until I finish this level, and they keep going and going and going and going and going. Next thing you know, they have a blood clot. There was a story not too long ago of a 22-year-old college student who died from developing a blood clot from playing a marathon. I can't remember what game it was. I don't remember if it was World of Warcraft or something, but he was playing one of those games, and he played it for like, I think it was 19 hours straight, and he formed a blood clot, and then it caused a pulmonary embolism, ended up dying. I'm not going to die for a video game. I love it just as much as the next person. Any other activity that keeps your legs bent? Prolonged bed rest. You know, you guys are in the hospitals. You get people up and moving. They can't lay there for too long. You get them up and moving, especially after surgery, because the incidence of blood clots forming is very high after surgery. And so you got to keep that blood moving, or you put them in that machine that squeezes their legs. Poor circulation, varicose veins, pregnancy, birth control. You hear about birth control thickening blood and making it easier for blood to clot. So if you're on birth control pills, that increases your risk of blood clots happening. If you are taking hormones for menopause, that can increase the thickness of your blood. And then you got cancer and trauma as well. But blood clots is one of the top reasons why people die. And it's one of the top reasons why people die in their sleep is blood clots becoming, you know, embolisms, that sort of thing. Because when you're sleeping, you're not moving around very much. And if you have poor circulation, or if you have some kind of medical issue, the chance of you forming that blood clot goes up. We'll talk about this more on Monday. I know I kept you about 8 minutes longer, but we're done. So it's all good. Ooh, that video looks kind of cool. How varicose veins. So this is valve incompetence. This right here, it looks like it's a little video there talking about how they might repair the valves. Yeah, look at that blood just collecting there. Stuck. Doesn't go anywhere. So get up and do some calf raises. Get up and walk around. Run something, you know, run often, or just do exercising, because it does help with the blood flow. All right, so you got the 7 o'clock class off. Take your test, prepare for your test, whatever. On Monday, we will do a couple labs, and so I'll shoot you an email this weekend to remind you. If you have any questions, email me in the meantime.
Thank you.
Thank you.